I'm always ready, Brady.
All right, so we are on page 470, where it says projecting one vector onto another. So if I have in a plane, I have a vector that looks like this and a vector that looks like this. What we're talking about is we're going to shine a light here onto this vector and project it onto this vector. So we're projecting, so if we call this vector A, we call this B, we are going to project A onto B. Make sure you get this nomenclature straight. Okay, so you are projecting A onto B. Okay, so look at the middle there where it says projection of the vectors. Okay, so if you're going to project, so the book says what? U to V. So I'm going to project the U vector onto the V vector, right? The projection is going to have the same direction as which vector?
V.
V, right? Because you're projecting it onto the V vector, right? So this is going to be the same as V vector with some sort of ratio here, right? With some sort of ratio. And the ratio is going to be dot product. And then you're going to have...
It's out of here. No, I said U. That's a U. Oh, I said V.
Okay, all right.
No, but not the second one.
Did you say A?
What?
Caden doesn't
know what it's saying.
Okay, so when I project U vector onto V, I'm going to have the same direction as V vector. So that's why this V is here, okay? All right. And then you're going to have the U dot V on top divided by the magnitude squared of V. Okay, so that's the equation, okay? So let's see if we can actually do this. Let's look at example number 5. Find the vector projection of U onto V. So we're going to have U onto V where U is going to be equal to, what was the U vector? 6, 2. And then we have the V vector being 5, -5. So I'm going to project this vector onto this vector. So again, I'm going to project the U vector onto the V vector. And I'm going to be U dot V. So U dot V 30 minus 10, right? 30 minus 10, so it's going to be 20. U dot V over V dot squared. So it's this guy, the magnitude is here squared. So it's going to be the square root of 5 squared plus 5 squared, and this guy squared, and then times it by the V vector, like that. Okay, so I'm going to get on the bottom, what am I going to get here? Well, this is root 50, then I have to square it. So it's going to be 50 again, right? So I have 20 over 50, which is 2 over 5 times this, which is going to be 2 -2. Okay. Yeah. Again, you have to make sure you get the nomenclature here correct. Okay, so that's example 5. Let's try example number 6. Example number 6. Juan is sitting on a sled on the side of a hill inclined at 45 degrees. Combined weight of Juan and the sled is 140 pounds. What force is required for Rafaela to keep the sled from sliding down the hill? Okay, so you have a hill where this is 45, this is 45, and on that hill you have a guy here, and the combined weight is 140 pounds, right? 140 pounds, okay? And Rafaela is pulling this way. Okay, so you're going to project this vector on to this vector here. Okay, because this vector here is going to be what? This here is going to be the same as this guy, no?
Yes.
Because they have to be equal so it's not moving, right? Okay. So what is the direction here? So I have 140. So this going guys going to be 140 divided by root 2. Does anybody see that? Because it's 1 to root 2. Right? So if I divide this guy by root 2, it'll be this guy, right? We good? No, not really. Kind of, maybe. So what are we trying to find? We're trying to find the force vector there, right? So let me use the same nomenclature that we're using here. So they called this F1. Okay, and we're going to project this guy. And they called that what? F. Okay, so we're going to project F onto F1. So what was F? F vector is going to be equal to what? Anybody tell me? What's the X component here? There is no X component, right? Because it's going straight down.
Yeah.
The Y component is what? 140, but it's going down, correct? So it should be negative. You good? F1 is going to be what?
No.
Because we're going to project that onto which vector? This guy is 45 degrees, right? So it's going to be basically 1 and 1, correct?
What's 45?
1 and 1, right? What is 45 degrees? Okay, I'm losing you here. I'm losing everybody here. Yeah, so it's because this guy here, if you look at this guy here, this guy is 45, correct? Right? So if I blow that up, it's going to be 45 degrees here, right? So I'm going to have I plus, this is J, correct? In the standard vector form, right? Or 1 and 1, right? 1 and 1, right? If I had the vector, if the vector looked like this, what would it be? Wouldn't it be -1 and -1 instead of 1 and 1? Right? So I'm going -1, -1, right? On this one, I'm going 1 and 1. So I get 1 and 1. Okay? So you're going to project this vector onto this. Right? So let's go ahead and do that. Projecting, whoops, PR, OJ. I'm going to project this guy onto this guy, right? So F onto F1. Okay, so I'm going to get the dot product of these two, which is -140. Can we see that? These two over, so this guy's going to be 1 and 1, right? Then over here I have what? This guy squared, correct? So it's going to be 1 plus 1, and this guy is squared. So what do I get on the denominator?
1.
2.
Oh.
So I'm going to get -70, 1, 1. Look. What do I do? What am I missing here?
I'm very confused right now.
I think we should just not do this.
-140 is correct.
And then root 2 over.
Where do they get these?
Instead of 1 and 1.
Instead of 1 and 1, they had root 2 over 2. And then they multiplied that 2.
Instead of the blah, 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 minus v squared is 1. Oh. Oh, I see what they did.
We use cosine.
It should be the same, we should end up with the same result though. Yeah, we're good.
That's
Because they have this as 1. And isn't that what they did here?
Yes.
Which is the same thing we have anyway, right? No, it's not. What?
If the teacher can't do it, why are we doing it?
Exactly, Hunter.
Hunter's hungry.
So they are using this as 1. Instead of 1, they are doing this, which is the same thing. And they're doing that, and I do this, I get 1. Okay, yeah, we're good. All right. So they're using this as a unit vector. Okay, so they're doing root 2, 1 over root 2, 1 over root 2. Okay, because it's the equal amount, right? That's what makes it 45 degrees. When this and this is the same. Okay, so I get it. We're good here. So if you add this, you're going to get square root of 1/2 plus 1/2. And this guy here would have been, so root 2. This would be 1, negative 140, which is negative 140, root 2 over 2, root 2 over 2, negative 70 root 2, negative 70 root 2. Okay? We good? We good? I hope we're kind of good there. Example number 7, work. Okay, so work, let's look in the middle there. Go ahead and read that middle paragraph where it says work and how they define work. Okay, so work done by W, work W done by F in moving the object from A to B is that. So the work is going to be the magnitude of F, the force, times AB. I mean, the vector AB. And so it's a dot product, basically. So the work is going to be defined, the work is defined as the force vector, the dot product of the distance or where it traveled, the path that it traveled. Okay? So let's go to example number 7. Find the work done by a 10-pound force acting in that direction. Okay, so I have a 10-pound force that's acting in 2, 1, is it? Or 1, 2, 1, 2. So the force is going to be 10 pounds, but I need a unit vector here, right? It's because the magnitude is 10. So I need the unit vector of 1 and 2. The unit vector of 1 and 2 is 1 and 2 divided by square root of 1 squared plus 2 squared. Right? So it's going to be 1 over square root of 5, 2 over square root of 5. So that's my force vector. And then I'm traveling from 0, 0 to 3, 0. So work is going to be this. And dot product of 3, 0, because that's where I'm going. 30 root 5. This guy is 0. So this is going to be 6 root 5. Everybody see where that's 6 root 5? You multiply top and bottom by root 5, right? Now the bottom 5 and this cancel out to be 6, so 6 root 5. Which is 13.42. And we are done. Now that we are done,